Okay, we are going to do section 7.1, parametric equations. So first, let's define what a parametric equation is. Imagine an ant or a particle or something walking along your piece of paper or your screen in, let's say, 2 dimensions. Imagine it following along the graph of some function. F of x, maybe it's a sine function, a parabola. As it's walking, you have a timer. At any given time, let's say just time is bigger than or equal to 0, the ant is at the coordinate pair, some other function to do with t in the x component, and then some other function to do with t in the y component. So x and y are the coordinates that depend upon time themselves. So they are their own function. So the way you can think of it is this graph that you see right here is the path the object takes. But there is a timer going on, my parameter, we're going to call it t for time. And so as time moves on, the x comma y ordered pairs are changing of that object. So another good way to visualize it, we can do a graph here in Desmos. Very similar, there's an x of t comma y of t, and there could be a location of the object at any given time. And then there's just a timer sort of being kept off to the side, but as time goes on, the location of the object changes. So both the x coordinate and the y coordinate of the object changes. So each of them might have their own function as time moves on. Okay, that's the definition of a parametric equation, and oftentimes it'll be called parametric equations, plural, because I have one both in the x component and in the y component. And then again in the z component if we were going to do this in 3 dimensions. Okay, so for example, let's just have a quick, easy example right here. Let's graph this parametric set of parametric equations by hand. So there's more than one way to do this. The easy kind of fallback way would be to create an XY table, the same way that you created an XY table the first time you ever learned how to graph things. The main difference though now is I have actually a third variable, and that would be t for my parameter or my time. Now here's an example where t, my parameter, is going from -10 to 10. So this is the independent variable, and both x and y are the dependent variable. So the independent variable is what I'm going to make some choices on. I'm just going to choose maybe -5, maybe -3, maybe 0, maybe 2, maybe 5, maybe 10. So I'm just choosing some. These are just some random choices that I'm making that are in between my domain on the independent variable. In this case, t was going from -10 to 10. And then what I'm going to do is just fill in that table of values by plugging those into the actual equations themselves. So 2 times t, if t is -5, then the x component would be 2 times that, which would be -10. And maybe I'll show that in a different color. There's your -10. I'll do all of the x components, and then I'll do all of the y components. So x depended on t, so 2 times 5, and 2 times 10. So those are all going to be, there it goes, sorry about the delay there. Those are all the x components at any given time or parameter, and then we'll do the same thing for the y. So 3 times t minus 4, we can use our calculator for that. 3 times -5 minus 4 gave us -19. Oops, sorry about that, -19. And then let's do 3 times -3 minus 4, and I got -13. 3 times 0 minus 4, 3 times 2 minus 4. It's good to notice really quick that we are plugging in the t into the y equals, not the x, because y does not depend upon x right here. In fact, y depends upon t. Okay, so maybe I'll make a note of that really quick here. That's actually 3 times the t variable, or the t value, minus 5. So I would have gotten 3 times 5 minus 4 gives me 11. And then the same thing here, 3 times 10 minus 4 gave me 26. Okay, so that's just like the XY table. And what I want to do is I'm going to graph that XY table. It certainly won't be perfect because we're doing this by hand, but I'll give it a good idea of the visual here. I just want to point out that the only thing that you're graphing is the x comma y. So you're not actually graphing time. Time is the timer. What I'm graphing is where the object is at those times. So -10 comma -19 is maybe somewhere down here. That was my -10 in the x component. -19 in the y component. And then I have a -6, -13. I'm not going to keep drawing all of the tick marks, but you can imagine what's happening there. And then 0, -4, and then 4, 2, and then 10, 11, and then 20, 26. Maybe I'll draw that last one with the 20 and 26. And then I could have done a whole lot more, so you can imagine I'm going to connect these dots. I don't really know if it's going to be a straight line or a curve right now, but what I do know is the orientation. This is something our functions did not have up until now. I have an orientation. Because I have a timer going, time moves forward and not backwards. So I'm not starting at the top right and moving down. Instead, I'm starting at the initial time value. So I have to be really careful. I'm actually starting way over here where my initial time value was -10, which would have been way down over there. And then I would have connected the dots in that direction. That's kind of really important to notice, that in that direction. So there was going to be this correct direction here. And the way we denote that is with those arrows. That would be the positive orientation of this set of parametric equations. Okay, ta-da. Now, how do I know if that's going to be a straight line or not? That's something else that we're going to have to do. So I know that was all this example says, was to graph that set of equations, but I'm going to kind of shrink that down, give myself some space, and show you there's more ways for me to understand the shape of that graph. Maybe it is curvy. Maybe I just did a really bad job here of graphing it. Maybe it is a straight line and I just can't tell right away. So we're going to figure that out. And so I'm going to rewrite my set of parametric equations. I have x equals 2t and I have y equals 3t minus 4. And then I'm going to show you that I can actually eliminate the parameter. So I'm going to write that down so you see what we're doing. Eliminate the parameter. And the way I do that is exactly as it sounds. You get rid of or eliminate the parameter, or t. So I'm just going to solve for t and plug it into the other. So this will become x divided by 2 equals t. And then I'm going to take that and plug it into the other. And that will give me y equals 3 times x divided by 2 minus 4, which I can simplify as 3/2 x minus 4, which you can see is a straight line. That's a y equals mx plus b. So that is a straight line. It was kind of hard to tell at the beginning, but in this case, now I can tell it actually is a straight line. And if I were to graph the function y equals 3/2 x minus 4, it would look like this. That line, however, by itself is infinite, but ours is cut off because I have a beginning and an ending time value. So this would have been my time equals 10, and this one way down here would have been my time equals -10. So this is a line segment. Okay, let's do another one. The more, the merrier. Let's do a few more. So graph the set of parametric equations, then eliminate the parameter to obtain an equation in x and y. So I'm going to do the same thing that we just did. I really am going to do the txy table. This is always going to be your really good default to get a visual and a good understanding of what might be happening. Your t is the independent variable, so that's the one you get to make some choices on, which in this case, t goes from -4 to 4. So maybe I'll choose things like -4, -2, 0, 2, maybe 3, maybe 4. I just chose some symmetry here. These are choices, right? Because t was independent, those were choices. They just needed to fall within the given domain. And then I'm going to plug each of those into both the x and the y. So x is t squared plus 2. So that would become -4 squared plus 2, which is 18. And then x is x is 2t squared plus 2. So if t is -2, -2 squared plus 2 is 4 plus 2 is 6. And then I would get 0, and then I would get 6, and then I would get 18. That was me plugging each of those time values into the parametric equation for x. And then I'll do the same thing for y, and y in this case is just 4 times t. Remember, it's 4 times t, not x. That's an important distinction. So 4 times -4 is -16, and then 4 times -2 is -8, and then 0, and then +8, and then +16. And then a quick note one more time, what you're graphing is not time. What you're graphing is the location of this object at any given time. So let's go ahead and graph this guy. Here's my X and Y. So the ordered pair 18 comma negative 16 is the starting point. So I think it's always worthwhile to label at least the starting and ending point. That's the good justification for what might be happening. So I'm going to label that one. That was at my time equals -4. So that's the starting point. And then I have 6 comma -8. So 6 comma -8 looks a little something like that. And then 2 comma 0, I'm not labeling every single one. And then 6 comma 8, and then 18 comma positive 16. I am going to label the beginning and ending time values. And when I connect those, the direction mattered because time moves forward, not backward. So those arrows are indicating what is called the positive orientation. And we say positive orientation just not because t is positive, t could be negative, but because it moves in the positive direction. It only moves forward rather than back. Okay, cool. All right, so now we have graphed this. Fantastic. And it's also important to notice, it's really important to notice that there's not arrows at the end or beginning of that parametric curve because this is a stopping point. I've stopped. I'm not going on forever. Time is not infinite in this particular example. Okay, there was more to this question though, so I'm going to give myself some space. Let's answer the other part, which is eliminate the parameter. So I'm going to rewrite my set of equations, x equals t squared plus 2 and y equals 4t. The way to eliminate the parameter is to solve for t and plug it into the other. Now, it doesn't actually matter which one you solve for t. So I'm going to choose the easier one, which would be this one over here, the y. If I were to divide both sides by 4, I got y divided by 4 equals t. And then I can plug that into the other equation, and I'm going to get x equals y divided by 4 squared plus 2, which I suppose I could simplify to be x equals 1 over 16 y squared plus 2. So I have eliminated the parameter, and hopefully you notice the shape there. That is the equation for a sideways parabola, which makes perfect sense. I had a sideways parabola here. Ta-da! Let's do it again. Repetition is key. Now I'm going to ask you to eliminate the parameter first and then draw the curve, because you can actually solve that in the other order, which I think is totally fine. So let's eliminate the parameter first. Here's a classic example of one that looks like it should have some kind of curve to it, like the square root function. We think of square root functions that have that slight curve to it, but that doesn't necessarily hold true for parametric equations every time. So here I have x equals the square root of t plus 4, y equals 3 square root of t. Solve for t and plug it into the other is the general idea for eliminating the parameter. However, you really just need to eliminate the parameter. You don't actually need to solve for t. You just oftentimes ended up solving for t sort of by accident, right? So what I'm going to do is I'm going to divide both sides of the y by 3. And if I did that, I would end up with y divided by 3 equals the square root of t. Now, I could square both sides if I wanted to, but I don't need to because I have a square root of t in my x equation. So I can just completely replace the entire square root of t with just y over 3. And then that's going to give me x equals y over 3 plus 4. Now that's a straight line. Now, sometimes it's hard to imagine straight lines when you have it written as an x equals, at least for me, I know it is as well. What I mean by that is we're used to having things written as a y equals, so I am going to have to graph this, so I might as well do the work to get y by itself because that's what I'm used to. So I'm going to multiply both sides of this equation by 3, and then I'm going to subtract 12. So I got y is equal to 3x minus 12. That's like your mx plus b. It tends to be a little bit easier to graph when things are written as a y equals. Okay, so let's do that. So y equals 3x minus 12. That has a y-intercept of negative 12 and a slope of 3. So that means it goes up 3 and then over 1, right? So up 3 over 1, and then I draw a dot. Up 3 over 1, and then I draw a dot, and so on and so on. So I'm going to draw that, pretend I'm a really good artist. There it is. There's my straight line. And then you have to pause and think about what it is that we're missing. we haven't yet considered the domain of my parameter. So in this example, t only goes from 0 to 16. So this is not going to be an infinite line. It's going to have to cut off somewhere. But where? Well, it starts off when time is 0. That is not the same thing as x equals 0. That is not the same thing as x equals 0. That's important, okay? So if I think about it, plug in time equals 0 into the x equation, and I'm going to get the square root of 0 plus 4, which is just 4. So the x value of 4, plug it in into the y equation as well, and you're going to see that the y is 0. So at the ordered pair 4, 0, that was my time equals 0. And then if I were to plug in 16 into each equation, the square root of 16 is 4 plus 4 is 8. And then the square root of 16 is 4 times 3 is 12. So 8, 12, this was my 8, 12. That corresponds to time equals 16. So in fact, this is the actual line segment. Everything else is gone. So that's something to remember there, that restricted domain on the parameter tells you whether or not you have an infinite curve. If you only have a part of it, what is the actual piece that you're drawing? Excellent. And when I say indicate the positive orientation, those arrows is enough. That's indicating the positive orientation. Okay, let's do another one. So same kind of idea for part B. Let's eliminate the parameter and then graph this using the same strategies that I just did. To eliminate the parameter, you could solve for t and plug it into the other, or you could just solve for this like thing that's in common between the two, which in the previous example was the square root of t. And here in this example, I have x equals e to the 2t and y equals e to the t plus 1. So the e to the t is this thing that's in common. So I'm going to solve for e to the t, which is y minus 1. And then I'm going to plug that into the other. And if you notice, I have x equals e to the 2t, which is the same thing as x equals e to the t squared. So now I have x equals y minus 1 squared, which we know is a sideways parabola. Okay, so now I've eliminated the parameter. That's really good. Now I have to graph that, the sideways parabola. Also, that's a sideways parabola with a shift of 1 unit in the y direction up by 1. So I'm going to graph my sideways parabola and pretend I'm a really good artist. That was my, that was close enough. That's my sideways parabola, but I need to remember now my restricted domain. In this case, t only goes from 0 to 25. So if I were to plug in 0, it might be worthwhile to notice how to plug that in. So I'm going to write that out. So at time equals 0, my ordered pair is going to become e to the 0, which is 1, and then e to the 0 plus 1, which is 2. So 1, 2, here's my 1, here's my 2. That's the starting point. And then again at the ending point, so at time equals 25, I'm going to plug in 25 into my x equation, and I got e to the 2 times 25, which is some really ridiculously large number, and I don't need the decimal, but it's some large number. And then e to the 25 plus 1 is going to be my y component, which is another large number that's not quite as large, but still very large. But somewhere way up here, this was my at time equals 25, and then this is the time equals 0, which means now you know the order, the direction of travel, and you know the rest of that parabola was not part of the graph. Ta-da! Okay, let's do a little bit more. So the description, the positive orientation, you can always go back to do the TXY table. That's always a guarantee. So another example, eliminate the parameter to find a description of the following circles or circular arcs. Here I am giving you a nice little hint and telling you that these are in fact going to be circles. And then give the center of the circle, the radius of the circle, and make sure you draw that and indicate your positive orientation. So again, let's eliminate the parameter. You could solve for t and plug it into the other. Now I'll start that off really quick. I could make this x divided by 3 equals cosine of t. And then I could say arc cosine of x divided by 3 equals t. This is not a good path to go down because once you do the inverse trig, you now have kind of restricted domains. You have to think about domains of the inverse functions and ranges, and it gets a little bit more complicated. So you don't want to do that unless you have no other choice. I have another choice here. So here's kind of a cool trick for this particular problem. I'm going to take my x and I'm going to square it. And I'm going to take my y and I'm going to square it. And I'm going to add the two together and I'm going to see what happens. Here's a nice little trick for sines and cosines because sines and cosines have really nice trig identities when things are squared. So that was the reason for doing this. So my x is 3 cosine of t, and then I'm going to square it, plus my y is 3 sine of t, and then I'm going to square it, and I will continue simplifying this. This becomes a 9 cosine squared of t plus a 9 sine squared of t, which in this case I can factor out the 9, and I'm left over with a cosine squared plus a sine squared, which we know to be 1. So I ended up with the equation x squared plus y squared equals 9. I eliminated the parameter. Not only did I eliminate it, that is clearly a circle, and we know that is the circle of radius 3, and that circle is centered at 0, 0. Let's graph it. Okay, this is kind of a classic one, by the way. This is a classic Calc 2 question. Being able to do those circles is going to be very, very, very useful. So definitely practice lots of these. And I've got a few more of them to do as well. But I do need to do the graph. So let's start with the graph. I'm going to recommend that you start off just graphing the circle as it is and then worry about the time after or the parameter after. So I have a circle centered at 0, 0, and then its radius is 3. And pretend I'm a good artist. There's my nice, well, that wasn't even super great, but pretend it was perfectly centered. Let me erase those dots because I clearly didn't do it to scale to begin with. But there's my circle. Fantastic. I need the order, the positive orientation. So now I think about the time. And here's where it is a little trickier to do in your head. It really is. So you can, if you can do it in your head, you're loud, like totally fine, but I don't recommend it. So here's what I recommend you do, especially for these circles or for anything that got a little bit complicated. If the exponentials or the logs, they get kind of complicated. The TXY table is your guarantee. So go back to that. This is the guarantee. So start with the lowest time value and then pick a few time values that are a little bit higher. So in this case, I'm starting at pi, and then I need to end at 2 pi, and I should pick a few values in between. Okay, so pi is 3.14. So maybe I choose like 4 and 5 because 2 pi is about 6 something or other. And it's because we have a calculator, so it's totally okay if we're just estimating here. Just make sure that your calculator is in radians mode. Make sure your calculator is in radians mode here. And I'm just going to plug each of these values into my x and y. Okay, so 3 cosine of pi. Like literally 3 cosine of pi into my calculator. You don't have to do it all in your head. Or you could know your unit circle, which I hope we do, and that's okay. I got -3. And then I'm going to do the same thing for the y. 3 sine of pi. Again, you can use your calculator. I got 0. So -3, 0. Here is my -3, 0. That's my starting point. Then I'm going to plug in the 4. So 3 cosine of 4. I got -1.9. And then I'm going to do 3 sine of 4. I got -2.3. 2.3, sorry. And then I'm going to do the same thing. So I got 3 cosine of 5. And I got, yeah, there it is, 0.9. And then 3 sine of 5. And I got -2.9. Sorry for the sloppy handwriting there. And then if I plugged in 2 pi, I ended up with 3, 0. So I'm going to plot each of those points. So the next point was the negative 1.9 comma negative 2.3. That looks like about here. And then it was like about here. And then it ended here. And then I follow in the direction where time is moving forward to get that positive orientation. And then I know in this case, it was just part of a circle. So a semicircle. And it had this orientation of the counterclockwise orientation. Cool. All right, let's keep going. Let's do another one. Let's do another example. The next one, part B, same idea, the exact same idea, except for I have some extra numbers. So it does get a little bit trickier, but we can do it. So you can't use those nice, cool trig identities until you have just a sine squared and just a cosine squared. So you do need to do a little bit of a manipulation to make it so that you can get just a sine squared and just a cosine squared. So I'm going to rewrite that x equals 1 minus 3 sine of 4 pi t to write it as x minus 1 equals 3 sine of 4 pi t, and then y minus 2 equals 3 cosine of 4 pi t, and then I'll square both sides. So I'll do the x minus 1, the entire quantity squared, and then I'm going to also do the y minus 2, the entire quantity squared, and that will give me the negative 3 sine of 4 pi t squared, plus the 3 cosine of 4 pi t squared. And then we continue this simplification here. Now I can get a 9 sine squared of 4 pi t plus a 9 cosine squared of 4 pi t. Factor out the 9, and I would be left over with sine squared plus cosine squared, which is just 1. So then I ended up with x minus 1 squared plus y minus 2 squared equals 9. This is a circle, and this circle has a center. It's shifted now to 1 comma 2, and this has a radius of 3, or the square root of 9. Okay, so now I can draw the graph. You have a nice eliminated the parameter. Now we will draw the graph of this. And in this case, it is a circle. I'm going to draw this a little bit more carefully here. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, and I've got my center at 1 comma 2. And then my radius is 3, which means I just need to go 3 units all the way around. So I'll go 3 units up and then 3 units down and so on. 3 units up, 1, 2, 3. 3 units down, 3 units over, 3 units over, and then connect my circle. And it was close enough to a perfect circle. Okay, as close as we're gonna get, I think. All right, so now that we have that, we also have to go back and look at my parameter, my restricted domain. And like I said, when things get a little complicated with lots of x's and y's and sines and cosines and e to the x's and exponentials and anything like that, your default should be the TXY table. All right, because that's going to be a guarantee. It's going to be a guarantee, and you get a calculator so you can create it that way. It's nice and easy. So I'm going to pick my values. I got 0. And then I need to end at 1/2. In this case, my time went from 0 to 1/2. So you need to pick a few values. You can't just pick one. You really can't. Because what if, this is a good time to pause what you're writing and just watch with me. If I started right here, let's just say time equals 0 was right here. And then let's just say that time equals 1/2 was also right there. And what if what if one other point gave me right here? Then I wouldn't know if I'm going up or if I'm going down. So you need to pick multiple points, is what I'm saying. You need to have multiple points in your TXY table. So maybe you just choose a couple of them, like 0.1 and then 0.2. Okay, you get a calculator, so you can totally just use your calculator to plug that stuff in. So where do I plug that stuff in? I plug 0 into the x equals. That's very important, into the x equals. Sine of 0 is 0, so I got 1 there. Cosine of 0 is 1, so I got 5 there. Okay, then I'm going to plug in 0.1 into this x equals, and I'm going to use my calculator for it. So I have 1 minus 3 sine of 4 pi times plugging in 0.1. And I got the decimal, let me write it, of negative 1.9. And then I'll do the same thing for the y. So 2 plus 3 cosine of 4 pi times 0.1. And I got 2.9. positive. So then let's graph those two really quick. Let's graph those two really quick to see what happens. So the negative, the 1,5, 1,5 is this point right up here at the very top of the circle, it looks like. So that was my time equals 0. And then negative 1.9 comma 2.9 looks like it's like right there somewhere. So that tells me the orientation. Fantastic. Now we have a really good orientation. I'll plug in the rest of them as well so we have it. Negative 0.7. This one gave me negative 0.4. So negative 0.7, negative 0.4, looks like it might be right around there. So we just kind of continuing along that path, which is good to know. Plugging in 1/2. I already plugged in 1/2 in my calculator as well, and I got 1,5. So that means it ended right back to where I started from. So in this case, it happened to be a full circle with a starting at the top of the circle and oriented counterclockwise, and it's also shifted a little bit. All right, we are on a roll with these parametric equations. So I have another example. The path of a point on some circle, let's call that circle capital A, with a radius of little a over 4, that rolls on the inside of a circle, we'll call that B, with the radius A, has a name, it's called a hypercycloid. Its parametric equations are given by this, so I've got x equals a times cosine cubed, and y is equal to a times sine of cubed, and we're going to do where t goes from 0 to 2 pi. It's basically completing one full cycle. Let's graph this and find its equation in terms of x and y. So I'm not going to make you graph this one by hand, but I do want to show you. I'm going to only graph this, find the equation in terms of x and y. But I do want to show you what the graph looks like so you have an idea. So here is just this graph in Desmos. So before I graph the whole cycloid, here is just two circles, one circle inside of the other. Right, the big circle, the one in green right there, has a radius of 2. The small circle, the one in purple on the inside, has a radius of 1/2. Okay, so there's just one circle inside of the other. And then I'm going to take the small circle and I'm going to roll it around on the inside of the big circle. And as I'm rolling it around, I'm going to, before I start rolling it around, I'm going to have a pen that is holding one spot steady right through that circle. And it's just going to move with the purple circle, and it's going to trace out where that one point on the purple circle or on the smaller circle, it's going to trace out that path. Okay, and then that's the path that we're going to be dealing with, and that's the path that you see there in red. You can see as I roll around one circle inside of the other, that I am tracing out this weird little diamond shape that is called a hypercycloid. And it's also cool. This is one specific example of a hypercycloid. We can change things up a little bit, and as things change up a little bit, the cycloids get stranger. And they definitely get a little bit stranger. So it's just kind of cool to realize that you can draw all kinds of amazing stuff with parametric equations. Okay, so this was one cool example, but let's do the actual math that we need to do. I want to find its equation in terms of x and y, which is a fancy way of saying eliminate the parameter. So I'm going to rewrite my equations. I have x equals, first of all, it tells me a is 2. So 2 cosine cubed of t, and y is equal to 2 sine cubed of t. I could divide both sides of each of those equal signs by 2 to try to isolate my sines and cosines. And so I'll do that. The other thing that I can do is raise both sides of that equal sign to the power of any number I want. I can square both sides. What I should do, though, is raise it to the power of 2/3. And I'm going to do that to both equations, both the x equation and the y equation, to see what happens. On the x equation, I would get x over 2 to the power of 2/3 equals. And then you should see cosine cubed to the power of 2/3. The 3 cancels. And I just got cosine squared. Same thing for the y. I'm going to get y over 2 to the power of 2/3 equals. And then sine cubed to the 2/3. The 3 cancels and I just get sine squared of t. So you can imagine what would happen if I add the two together. X over 2 to the power of 2/3 plus y over 2 to the power of 2/3 is equal to cosine squared plus sine squared, which is just 1. So that was me eliminating that parameter. That's the equation in terms of just x and y, and you can pause this, go to that website that you have here that I just showed you with the cycloid, and try to graph this equation in Desmos. You'll see it's the exact same, which is kind of cool to see. Okay, let's do another one. All right, so now we have some fun examples. The next thing I'm going to do is find a parametric description to describe the movement of an object that travels along a straight line. So up until now, so far, I have been giving you the equations and you draw the graph. Now I'm just doing the opposite. I'm telling you the graph and you give me the equation. So that's another common strategy we need to be able to do. And I've given you a nice hint. So a common way to write, a common and a good way to describe a line would be the x and the y being linear. So like mx plus b. Except for I have time now, not x, so I did a plus b times t and c plus d times t. Okay, so find a parametric description to describe the movement of an object that travels along the line segment that starts here at 2, 3 and then ends at 5, 9. And I want time equals 0 to give me 2, 3. And I want time equals 4 to give me 5, 9. So let's just start off with what we have. I want time equals 0 to give 2, 3. That's what I want. So let's think about it. At time equals 0, what is my ordered pair? Well, let me write it nice and clear. My ordered pair is a plus b times t, comma c plus d times t, and I'm going to highlight that. All I did is I rewrote those equations as an ordered pair. You can always write an ordered pair out of the x equation and the y equation as the x comma y. So that's all I did. Then I'm going to set that equal to 2, 3. Okay, but what was my time there in this case? Again, my time was 0. So really that time should be 0. And then that simplifies quite a lot. So a comma c equals 2, 3 because those zeros canceled each other out. Okay, so then I ended up with a equals 2 and c equals 3. All right, we're getting somewhere. We're getting somewhere. Let's do the ending part. So at time equals 4, what would my ordered pair be? It would be, again, a plus b times t, comma, c plus d times t. I just wrote them down from my parametric equations. Okay, but then I have to realize that if time is 4, then time is 4. If time is 4, then time is 4. And I need my ending point to be 5, 9. Let's simplify. This will become I'll write it here first, a plus b times 4, c plus d times 4 equals a 5, 9, but I already know what a and b are. A is 2, and c was 3. I think I said that wrong, but I wrote it correct. I apologize. It's a was 2 and c was 3. And so now I have everything that I need to just solve for the unknown. So 2 plus 4b equals 5, and 3 plus 4d equals 9. And so then I solve for b equals 3. So b equals 3/4. And then let's write that correct. 4d equals 6. So d is equal to 6 over 4, which is 3/2. So now you know what your A is, your B is, your C is, and your D is. So then we have everything that we need. So X was A plus B times T, and Y was C plus D times T. So that is my set of parametric equations where if T goes from 0 to 4, I have drawn that line segment that starts at the ordered pair 2, 3 and ends at the ordered pair 5, 9. So it started here and then went that direction and ended here. Ta-da! Okay, so in general, you want to try to eliminate your parameter to help you visualize the shape of the graph. If you have sines and cosines, it's probably going to be a circle of some type. So you might think of trig identities. And then you also have this general idea of how to find the equation, parametric equation of a straight line as well. It's a good summary for that. All right, that's all there is for 7.1. Thanks.